All right, so continuing our calculations of energy quantization in the hydrogen atom, let's see if we can use Bohr's equation to answer this question. How much energy is required to remove an electron from a hydrogen atom in the ground state? So let's go back to the Bohr equation, the one for delta E, to see if we can figure this out. The equation that I gave you at the end of the last lecture is as follows for delta E. We have that constant, z squared over n of the final state squared minus z squared over n of the initial state squared. All right, so we know that we're talking about hydrogen, so z is 1 because that's how many protons are in hydrogen, hydrogen's atomic number. Now, what are the n values? What is the n of the initial state and what is the n of the final state here? That's the big question, and if we can answer that question, then we can solve this problem. So we want to remove an electron from a hydrogen atom in the ground state. Now, the ground state is the lowest energy state. That's n equals 1. So we can say that the initial n value is going to be 1 because that's going to be what the ground state is. The n of the final state is a little bit trickier. Let's read the question carefully. We want to remove an electron from a hydrogen atom. That means we don't just want to promote it up to a higher energy level. We want to take that electron and pull it away from the atom completely so that it no longer interacts with the nucleus at all. So we can approximate that by saying we want the final n to be infinitely far away from the nucleus. So I'm going to define NF as just a huge number. I'm going to say infinity. So can we take these values and kind of plug them into this equation? Let's try it. Delta E is equal to minus 2.178 times 10 to the minus 18 joules times 1 squared is 1, over infinity. Infinity squared is infinity. Minus 1 squared is 1, over 1 squared is 1. Aha! So what is 1 over infinity? Well, that denominator is very huge, so this approaches 0 effectively. So notice what happens here. I'm going to have, if that term is 0, this is going to be equal to, positive 2.178 times 10 to the minus 18 joules. And the whole reason I did that problem is so you can see where this constant comes from. That number is actually defined as the energy required to remove an electron from hydrogen atom in the ground state. The energy required to remove an electron from ground state hydrogen. So that's where that number comes from that we've been talking about all this time. So you guys can use this equation to calculate delta E values for hydrogen, but you should know that the Bohr model breaks down for elements that are larger than hydrogen. In fact, even for helium, there's more than 5% error if you try to apply that equation to helium. So the question is why? Why doesn't the Bohr model work for larger atoms? Why does it only work for hydrogen? Okay, so hydrogen only has 1 proton in its nucleus and 1 electron circling that proton. So you can imagine that larger elements are going to have multiple electrons. So if you have multiple electrons, they're going to interact with each other. They're going to have repulsive interactions with each other because like charges repel each other. So multi-electron atoms have complicated interactions between their electrons. And that is one reason the Bohr model breaks down. once you have more than one electron. The other major reason, which is what I want to talk about now as we're moving into the next section, is that electrons do not actually have well-defined orbits. So this is where that kind of elementary school version of the Bohr model falls apart. In the Bohr model, it looks kind of like an onion. We have nucleus at the middle and then all of these circular orbits. But I want you to remember the de Broglie wave equation. So 1924, Louis de Broglie figured out that electrons have wave-like properties as well as particle-like properties. And you can kind of interrelate them by calculating the wavelength of a particle with mass m and velocity v. So we talked about that in a previous lecture. That means that we can really think about electrons kind of in these cloud-like regions around the nucleus rather than in well-defined orbitals. Okay, so I want you to imagine electrons in clouds somewhere around the nucleus. And it was really Erwin Schrödinger who developed a wave equation. So the Schrödinger wave equation is the closest thing we get to kind of predicting where an electron is going to be in an atom. So the Schrödinger wave equation, we don't go into it in too much detail in general chemistry, but that is just how you can predict nothing more really than the probability of finding an electron in a given region of space. So this is an uncertainty as well. There's a Heisenberg uncertainty principle related to this as well in a given region of space around the nucleus. So basically, we don't have these nice circular, well-defined orbits in which we find electrons. We can calculate a probability that they're going to be in a certain area, but it's not as defined as you think. So the Bohr model is not actually very applicable to any atom except hydrogen.